All right, I think we'll get started. So remember, next week is exam week. We will have review on Monday. Bring your questions. Come and ask me whatever you want. I've posted some review slides in section 3. It looks a lot like our previous review slides, so you can check that out. We'll try and cover at least the topics today if we have time. Otherwise, I want to get you through all the material, but we'll definitely be through all the material at the end of lecture today that you'll need to take the exam on Wednesday. Same procedure, same format. Everyone's done a really good job getting their stuff in, or if you have a problem, you've let me know. And so, you know, nothing's going to change in exam 3 and exam 4 and for the final. The final is scheduled, so take a look at that. If you're overloaded, you need to let me know, because we're doing the final on Canvas just like we've done the exams. And so the registrar isn't necessarily going to reschedule the exam for you. You need to file the overload with the registrar to make sure you're all set, but then you and I work out when you're going to take it. So there is no standard alternate exam time, but if you're overloaded, I'm happy to just make sure I open a Canvas window for you, but I need to know about it because I control that Canvas window. The registrar is not going to do it. So anyway, going into this exam is a good time to look at your calendar from now until the end of the semester, figure out when your exams are. We're gonna just continue homeworks, PLAs, the usual stuff. Everyone should be in the groove. Same office hours as usual. I'll try and make those as consistent as possible. And then of course, if you have issues, if you have questions, you want more office hours, or you need an appointment, or we're getting towards the end of the semester and you're concerned about your grade, I'm happy to talk about that before the semester ends. It's really hard to fix that stuff finals week. It's really, really hard to fix that stuff after finals week. And so if you have any concerns, I want to address those in the next couple of weeks, because we still have a lot of points. There's still exams, there's still homeworks. And so you can still get in the groove with this class, but the clock is ticking towards the end of the semester. All right, any questions or comments before we get started? Good. So the last thing on the exam is polymer conformations, and we've started to dip our toes into what this means. And basically it's describing quantitatively how the polymer is coiled up. So on the first day of class, we talked about polymers as long, skinny macromolecules, right? That's what makes polymers special. And we always drew polymers as some sort of squiggle, you know, some sort of coil, some sort of drawing, but this doesn't provide a lot of information unless we put some mathematics behind it. And so we started with very simple descriptions of how big polymer molecules are. Contour length, what does the contour length mean? Fully extended chain length, what does a fully extended chain mean, and how do you calculate that for simple molecules? So these are definitions that you want to keep in mind, and you're able to both draw the polymer chain and then draw what length that is. And so in general, in the contour length, at least in this slide, is shown as a straight line. I like to draw it in terms of tracing the zigzags of the backbone to get the contour length, because it's really easy to see the difference between the contour length and the fully extended chain length for a real example, because we know these sp3 carbons are all 109.5. And so if we put our polymer in the planar zigzag, it's really easy to see the fully extended chain length, as long as we can do the trigonometry to get this distance. And the 1.54, of course, comes from the carbon-carbon bond length. And so it's easy to add all of these up. The trick to this, of course, is remembering that there's 2 bonds per repeat unit. So that was important when we made polymers in the first place. So at least for addition polymers or vinyl addition polymers, where we push 1 electron one way and 1 electron the other way, you're making a half of a bond. That's what this parentheses through the covalent bond means. A half a bond here, a half a bond here, 1 bond here. So there's 2 bonds per repeat unit. So we've calculated X bar N a lot, or the degree of polymerization, because we can get that from the molecular weight in the M0. But remember, for this calculation, you need to think about how many steps you're taking in this contour length or fully extended chain or random walk, etc. So you need to remember to count the number of bonds in the repeat unit in order to get these right. Otherwise, your answers, if you use the degree of polymerization, your answers will be 50% of what they should be. And you can bet that that is probably going to be one of your choices on the exam, because that's an easy mistake to make. Questions on this? Yes.
Repeat that again.
So the number of bonds is not the same as the degree of polymerization. So remember, we calculate the degree of polymerization from the molecular weight and the repeat unit molecular weight, the X bar N, the thing that we've been talking about for the whole semester so far. So once you have the degree of polymerization, which is N, you need to look into that repeat unit and figure out how many bonds are in that to calculate contour length, fully extended chain length, etc. So don't use degree of polymerization blindly. Think about it. All right. Great, we did that, we did that. We talked about if we just make a globule, that's fine. And I think we ended up something with freely jointed chain. So contour length is a definition. Fully extended chain is a definition. And freely jointed chain is a definition. So when I say freely jointed chain, I mean this model right here. So this is the freely jointed chain equation, and it gives us the RMS end-to-end distance. And so remember, we talked about this as equaling the absolute value of R, where R is the end-to-end distance. And it turns out in a lot of cases, just looking at a polymer that's all coiled up, and it might look something like this, characterizing that end-to-end distance is important. That's used in rheology, that's used in polymer physics. It's a really nice descriptor of how big the coil is, because it's hard to figure out the volume of this thing, right? It's hard to figure out exactly what's going on. Contour length and fully extended chain length aren't very realistic descriptors of what a polymer really looks like. And so we use this end-to-end distance as a descriptor of the coiling of the polymer chain. And the end-to-end distance will change depending on the situation. And of course, it depends on the molecular weight. So R, well, you're not going to see that, but R squared to the 1/2 is R, and that equals N to the 1/2, number of steps or number of bonds in the backbone, not the degree of polymerization, and then L. So what distance is L for polyethylene in this equation? Yes. Well, if you want to do it in nanometers, that's fine, but let's do it in angstroms. So yes. So it's 1.54 angstroms, right? And so, you know, it doesn't matter what distance we calculate. N is unitless, right? Because that just tells you the steps. That's the number of bonds, same as always. But in this case, we use 1.54 because we're taking steps per bond. What's the carbon away? And so we use the bond length in this equation. We don't use anything else. So the fully extended chain is special because we need to figure out what that shortcut distance is, but not in a lot of these examples, because we can think about taking a step, and all those steps are where the carbons lie on the backbone. Okay, great. So we have a really simple way to calculate the end-to-end distance of a model polymer. What are the assumptions of the freely jointed chain? So we have the bond length. That's not an assumption. We just looked that up. We have the number of steps from the degree of polymerization and the number of bonds in the repeat unit. That's not an assumption. But what does this model assume? Yes.
Go exactly back on themselves?
So it is self-avoiding. That's built into the random walk, although it doesn't have to be. It depends on how it's programmed. But what's the other big assumption? What's important about carbon-carbon bonds in terms of sp2, sp3? Yes?
They can rotate.
They can rotate, and they're tetrahedral, right? 109.5 is the angle with which you can take that step. In the freely jointed chain, you don't have that angle built into the information. So there's no angle in this equation, right? And that's why we call it freely jointed. That bond angle can be whatever it wants. So that's a really important assumption of the freely jointed chain model. And so the name of the model sort of reminds you what's in the model assumptions. But that's something that's going to be important because, you know, the assumption for contour length, there we go, is that it was all stretched out. The assumption for the fully extended chain length, that it's all stretched out in a planar zigzag. And so those are implicit assumptions in the model. And for the freely jointed chain, we make the assumption that we don't restrict the bond angle or rotation. We're just taking steps of length L. Any questions on that? All right, the next model that we're going to handle is called the valence angle model. And so this is still freely rotating, which means if I have a carbon-carbon bond at 109.5, I can assume any conformation that keeps the 109.5 bond angle. So in this case, the bond angle is specified. Conformations are not, or favored conformations are not specified. So we're not saying they're all trans, or we're not saying they're all eclipsed, or we're not saying they're all gauche, but we are saying that all the bond angles are theta. So usually that's going to be 109.5 because that's the type of sp3 carbon-carbon bonds that we're talking about in our backbone, but it doesn't have to be. And so now our model is this. Know what n is, we know what L squared is, and now we know what theta is, which is the valence angle of those bonds, or 109.5. And so now if you look at this model, what are we really computing here? What quantity is that? R squared, right? And so if we want R to compare to this R, notice that this is n to the 1/2 times L. And if we square that, we get n times L squared. And so if we really want to compare the end-to-end distance of the freely jointed chain and the end-to-end distance of the valence angle model, we have to take the square root of this whole thing. So make sure you know the difference between R squared and R. It's just the way the equations are written, but you can always go back and forth. There's a question. Was there a hand up? Yeah.
So it would be plus or minus. We can consider it between plus or minus. Thank you.
Has to be plus. Yeah, so that's why we square R, right? So if you take any number and square it, you'll get a positive number. Unless you have a rational number, let's not talk about that. But any positive or negative regular number, you will have a positive. And then if you take the square root, you get that number back. So remember, we discussed this last time, that R squared to the 1/2 is just a way to get a positive value every single time. That's the computational trick that you learned in programming in order to get the absolute value. We just don't write it as absolute value. It's called RMS. Same thing here. You're always going to get a positive value for R squared. And so if you really want to compare it to other R's, you just take the square root of that and you're all set. So we could write this r squared to the 1/2 sub FA, and we can put everything in there if we wanted to. All right, so what this model says, if we look at the situation, is now we have a fixed angle theta. That's why it's called valence angle, but we have free rotation. So there's no preference in the conformation of that polymer backbone. It just does what it's going to do. So comparing valence angle model to freely jointed chain, which one do you think is larger? So for the same exact situation, if you plug everything into the freely jointed chain and calculate R, and then you plug everything in, assuming that our bond angle is 109.5 degrees, you plug everything into the valence angle model, then you take the square root in order to get R. Which one do you think is larger? Yes. What's that? The freely jointed is larger. Okay, why do you say that?
Because 1 minus R theta, so 1 plus theta would be less than 1.
So that is a very good question. Is this quantity less than or greater than 1? And so I suggest you put your calculator in degrees. Make sure that's in there, right? If it's in radians, you're going to get something really funky. And then calculate this quantity. And you can figure out on your homework or on your discussion tonight why this one is larger or smaller than the freely jointed chain. Because that's the only difference between these two models, right? So check that out and you can take a look at that. All right, so the last model that we're going to talk about, and this is the last piece of information that you're going to need for the exam, is called the valence angle model with hindered rotation. What does hindered rotation mean? So the valence angle model was freely rotating. I can rotate my carbon-carbon bonds whichever direction I want. Hindered rotation says that there are barriers between these different conformations. And so hindered rotation is a more realistic scenario based on what we know about Newman projections and about the energy of trans and gauche conformations, right? This is hindered rotation because there's some energy minima. And so the polymer is going to spend more time in planar trans, gauche plus, and gauche minus compared to these other intermediate conformations. And so the valence angle part is the same as we've had before. We just put in theta because we know what that angle is going to be as long as we know the backbone. And then we build in hindered rotation through this steric parameter. And this steric parameter is measured. It's just fit to the model. We're not going to calculate it, and I'll show you a table of these steric parameters in a second. But now we can think about, okay, we have our valence angle model, and you're going to compare that to the freely jointed chain and figuring out if it's larger or smaller. Now we think about the steric parameter and what that means. And so is this, well, and I should tell you that these are a table of steric parameters right here. So all steric parameters are greater than 1. So sigma is greater than 1. And so if all steric parameters, sigma greater than 1, is the valence angle model with hindered rotation going to give you a longer RMS end-to-end distance or shorter RMS end-to-end distance compared to our valence angle model? If sigma is always greater than 1, what does putting sigma in this do to our R squared knot? Yes. Makes it longer, right? The end-to-end distance is going to be longer compared to the valence angle model. And that's a more realistic situation because we know that there's hindered rotation. We know in some cases there's substituents like polystyrene, right? So those rings are going to bump into each other. And so the valence angle model with hindered rotation stretches out the coil a little bit. And so R squared 0 is always going to be greater than R squared FA based on the definition that sigma is always greater than 1. What if sigma equals 1 in this equation? What do we have if sigma equals 1? The previous one, right? So it collapses down. All right. So those are important things to think about. What are the assumptions? Which model is going to give you a larger or shorter distance? And then the parameters are pretty easy to figure out. You'll look up sigma, you'll figure out what N and L are, and then you just have to keep your wits about you, whether you're calculating R squared or you're calculating R squared to the 1/2, so you can compare R's between the two. Questions? Yeah.
On an exam, would we be given sigma or like a table of them, of the values?
Yes. Yeah. There's no way for you to know sigma. You know, you should know theta. If I tell you you have polyethylene or polystyrene, you should know that theta is 109.5. I expect you to know the bond angle of sp3 carbon. If it's something funky that you're not going to know, I will tell you that, or you'll have a table, but you will have a table of sigmas to look up because there's no need to memorize those. Any other questions or comments? All right, so we have a number of different models, right? In just a few slides, we've covered contour length, fully extended chain length, freely jointed chain, that's 3 models. Valence angle model is 4 models. And then valence angle with hindered rotation. 5 different ways to describe what polymer chain conformations look like. So you should write down those 5 models, write down the key features of them, write down how they work and what they're describing, and make sure that you know the difference between them, because there will be a couple of calculation questions on the exam, but there could also be some conceptual questions on the exam too, right? And so make sure you're able to work your way through this and make sure that your calculator is in degrees and not radians, or else you're going to get really funny stuff. Okay, other questions or comments? All right, and so you can take a look at that, ask questions on Monday in the review. I'll cover it again on Monday and we're all set. All right, break out your clickers. So remember, the steric parameter is greater than 1. Whoops. Steric parameter is greater than 1, and it describes the hindered rotation. So a higher steric parameter is going to be more hindered rotation, right? So polymers that are stiff are going to be stretched out, have a higher steric parameter. Polymers that are more flexible are going to be collapsed in and have a lower steric parameter. So the question is, well, we're on CD. All right, that's working. Which polymer would you expect to have the highest steric parameter at a given temperature?
So was it AA instead of CD? Or is it still CD? I thought it said AA.
Really?
Yeah.
Oh, someone reprogrammed the thing. Okay. For anyone who's rung in, did you still have CD or did you have AA? Put everything on CD and we'll see if we get, you know, it only looks like there's about 45 of you out there. Looks like CD's working. I don't know what happened. All right. So which polymer would you expect to have the highest steric parameter? And highest steric parameter, high sigma equals stiff chain. And that equals steric hindrance. Okay, so is polyethylene going to have a lot of steric hindrance to its rotation? No, count that out. Now, the question is, there's a lot of R groups on here, right? And so which R group is the biggest? So what do you think? Who votes for C? Chlorine's got a lot of electrons, right? Is C the biggest? No, okay. What about D? Is that the biggest? No. So everyone's voting B, right? So why would you pick B? Just ballparking this. I mean, I didn't give you any measurements. I didn't, you know, they all kind of look the same size on this, why would you pick B? Yes.
Because on the first few days, you told us about how having the benzene ring means it's different.
That's right. So that's one thing. If you remember what polystyrene is, what's another way to figure it out if you don't remember all the way back? Go ahead.
A lot more atoms in B than there are in B.
That's right. So even though this ring looks pretty innocent, right? It's just sitting there. It's got a lot of atoms. Remember, it's got all those carbon atoms. So it's got 6 carbon atoms and 6 hydrogen. So if you're undecided and you don't know, well, what's bigger, what's smaller, I'm not quite sure, just count the number of atoms and go with the most atoms being the biggest thing. That tends to work. There we go. And so this, what property of the polymer might this relate to? Stiff chain. So if I have a stiffer chain, what's it going to be? Yeah. So stiff chains and crystallinity, there's, we need to know if the polymer crystallizes or not. Turns out polystyrene doesn't crystallize, right? It's amorphous polymer. Yes.
Glass transition time?
TG, right? So glass transition temperature. So stiff chain stiffness is related to TG. Was there another question? Yes.
So just to summarize, the bigger the actual atom, the bigger the actual molecule is, or the actual marker, the stiffer the actual chain is, and the higher the actual TG is going to be.
That's right. That's right. I mean, there's some other things in glass transition temperature. There's dipole-dipole interactions and other things that come up. And so, you have to remember those. But at least as far as we know now, all things being equal, not counting intermolecular interactions, we're just looking at the intramolecular interactions of this, right? This model is all within the chain. So this is all intramolecular, right? We don't have any energy between the chains. We don't talk about exactly what the functional groups are, if you have a strong dipole or not. And so based on that model, polystyrene is going to have the highest steric parameter as far as we know in this class. All right. Any questions or comments on that? All right. And of course, clicker questions, PLA questions. That's how I'm going to ask you questions on the exam. So you want to pay attention to those. All right. Next clicker question. We can get a sense for how stiff a polymer chain is from the characteristic ratio. This equation and all the model equations will actually be on your equation sheet. I'll publish that with the practice exam, which I'll remember to put up today or this weekend if I don't get to it today. And so the characteristic ratio is just this R squared 0 over NL squared, right? So we take our valence angle model and we can divide some things out and we can ignore the valence angle part of it, but we can get this characteristic ratio C infinity. So do you expect a stiffer polymer, that is higher or lower than a flexible polymer? So does C infinity follow the steric parameter or not? So you can ring in on that. So if you take R squared naught and divide it by NL squared, you're left with the steric parameter and the valence angle part, right? You're just left with this 2. And so the real question is, mathematically, is C infinity similar to the steric parameter or not? Or how will they relate to each other? You can ring in. Yes.
Well, it's just, was that a rhetorical question?
Oh no, well that's the question, so you can ring in, but go ahead, give us your take on it.
I was just gonna say the sigma value
correlates the higher the sigma value, the higher the C infinity.
That's right. So higher sigma equals higher C infinity. And so I might call these characteristic ratios, steric parameters on the exam. I'm not going to say C infinity. I'm not going to say sigma. So you want to associate the vocab word, get your answers in. You want to associate the vocab word with the variable, and then you'll just be able to look up this equation on your equation sheet. So remember how I do equation sheets. That will be there for you, but you need to know that that's the characteristic ratio, right? And you need to know all these other variables. All right. Questions or comments on that? Good. And so this is what the table looks like. And so you see the sigma. So you see the chain stiffness parameter, and then you see our characteristic ratio. And so they, in general, follow each other. And they're measured slightly different ways, but it's the trend that's really important. So you see polystyrene here has a large steric parameter and has a large characteristic ratio. Something like polyethylene has a smaller steric parameter and a smaller characteristic ratio. Does any polymer have a steric parameter of 1.0 on this table? No, it doesn't. Which means what? What is a, so steric parameter of 1 means that we have our freely rotating chain model, right? And any steric parameter greater than 1 means what? There's going to be some favored conformations, even in something simple like polyethylene, right? Because this steric parameter, sigma, talks about restricted rotation and talks about restricted rotation or hindered rotation around carbon-carbon bonds. So even polyethylene is going to have favored conformations based on this very simple model of just what's planar trans and what's gauche, and it's going to have some high energy conformations, which are not going to be favorable. And so we can say that the freely rotating valence angle model always underestimates the real length of a polymer chain conformation, right? This doesn't have sigma in there. We have the bond angle information. That's great. But the valence angle model freely rotating is always going to be less than the valence angle model with hindered rotation. You know, we can't think of a simpler polymer than polyethylene, right, in this model. And so if the steric parameter and characteristic ratio are greater than 1, even for polyethylene, that means that the most accurate model that we have so far is this valence angle model with hindered rotation. So this is as close to reality in terms of polymer conformation as we're going to get. Everything else is more and more idealized. Yes.
So on the homework, for example, template 30 part C, when I asked what the actual valence angle model, use that valence angle model. Should we use it with rotation, or should we just like use the actual one we went over earlier?
That's a good question. So this is the valence angle model. This is the valence angle model with hindered rotation. They have slightly different names. And so if it's not specified, if I just say valence angle model, that's this. If I say valence angle model with hindered rotation, that's that. So I might not say freely rotating. You see, freely rotating is in parentheses. So that's not formally part of the model name, but it's just to remind you what the valence angle model is. But if I want hindered rotation, I'll tell you about that. Does that make sense? All right. Other questions? Okay. So we have a few minutes extra. So that's all the information that you're going to need for the exam. And so we can go to the review slides. I'm going to update the review slides with office hours. We'll have extended office hours next week. Same as usual. I want to make sure everyone has a fair shot of getting their questions answered. I will update you on those. Everything else is the same. And so remember the topics for exam 3. We might have a little diene polymerization because that was right at the end of the exam 2 material, but we talked about dienes and we talked about coordination polymerization a little bit at the end. Remember tacticity and stereochemistry, how we started this unit, that's still in there. Ring opening polymerization. And then we did a lot on copolymerization and capital FA, small FA, capital FB, small FB. Here's a hint on the homework. So I gave you a table for the homework, and the first part of the question asks you about what if small FA is 0.5, and you all know if small FA is 0.5, small FB is 0.5, right? Equimolar. And then you can calculate big FA, and you know that big FA is 1 minus big FB. And so when I ask you the second part of that equation, I tell you that capital FA is 0.5, and I ask you to find small FA. How do you do that? So how do you do that homework problem? Yes.
Substitute FB 1 minus FA, and then rearrange to get FA.
That's right. So you need to take the copolymer equation, and you need to know that small FB is 1 minus small FA. And then you've got one equation and one unknown. So you know the reactivity ratios, you know capital FA is 0.5, and you need to solve for small FA inside all that algebra. And that takes a little while. I had some people on office hours working through that, or you can use Excel or MATLAB or whatever you want. I probably won't make you do that on the exam, right? Because that's a long problem. It's many steps, it's fraught with danger. So I'll probably just have you go forward, or I will give you a plot and tell you to interpret the plot based on, you know, if my capital FA is this, what does the small FA have to be? But that's a hint on the homework that you're going to have some algebra to do. It's going to take a little while. And so make sure you can get that, get all the reactivity ratios in the right spot, and make sure that you substitute FB as 1 minus FA. Otherwise, you'll never be able to solve that equation. Any questions on that? All right, so we did a lot of copolymerization, and we also had a lot of equations in the last 2 days on polymer conformation. So make sure you're up on your models, make sure you understand how those work, make sure you can write them down and solve them and know what they mean. All right, we have some more clicker questions. Extra clickers today. So what is the tacticity of this polymer? Just to refresh your memory. Just 2 back, 2 forward, 1 back, 1 forward. Do we care about that? Is that any sort of pattern that we know? No, you're tempted to assign it a pattern, right? But it's not isotactic. It's not syndiotactic. So in this class, that is definitely atactic. Great. So even though you might be tempted to say, oh, what's the pattern? If it's not perfectly isotactic or perfectly syndiotactic, it's going to be atactic. Now, in the real world, they will say that a polymer is 97% isotactic, or it might be 70% isotactic, or 70% syndiotactic. There are other ways to characterize tacticity that you'll learn about in your other polymer classes, and that you'll learn about how to actually measure tacticity using NMR or something like that. But in this class, everything will be 100% isotactic, or 100% syndiotactic, or it's atactic. It has to be one of those. All right. What about a polymer that's got no stereochemistry in it? What about like something like a symmetric monomer unit that, you know, there's no chiral carbons in the backbone? What do we call that polymer? We can say that it's not chiral at all. It doesn't have any tacticity. Some people might call it atactic, but more precisely, the polymer tacticity is not defined because there's no chiral carbons in it. Okay. So you all know that. All right, next clicker question. So connecting some of these concepts to properties that we just talked about, which would have a higher glass transition temperature, isotactic or atactic polypropylene? Which one is going to be more crystalline? Let's start off with that. So we have to do a voice vote on this because this is not the clicker question. But what polymer is more semicrystalline, isotactic or atactic? Isotactic, it's more regular, right? Any regular structure is going to be more semicrystalline. Isotactic is probably more crystalline than syndiotactic, and they're both more semicrystalline than atactic. Great. So this is not that, this is not crystallinity, this is asking about glass transition temperature. And so which polymer do you think has a higher glass transition temperature based on the tacticity? All right, get your votes in. There we go. So isotactic is going to have a higher glass transition temperature. Why would that be the case, knowing what we just learned about the steric parameter? It's stiffer, or there's more interference between the isotactic unit. So if we stretch it all out and it's isotactic, these Y groups, right, are the chlorine. This is PVC, right? Yep, or methyl, sorry, polypropylene. So these Y groups are the methyl groups. We have the same stereochemistry on each side. So these guys are going to want to bump into each other. And so it's going to have a higher TG than atactic, which is more randomized. Now, syndiotactic, the Y groups actually point at each other. And so there can be cases where syndiotactic has a higher glass transition temperature, but I didn't ask you that in the question. The best answer for the way that I asked this question is isotactic, because the chain is going to be a little bit stiffer because of the regular arrangement of those methyl groups. What polymer is this? Yep, that's right. You should have some of these polymers in your memory bank. Again, remember when we talked about ring opening polymerization, we talked about lactones, we talked about lactams. There was a little chemistry in there. And so we're going to review that on Monday because that was pretty packed with some new types of polymers. And so make sure that you're able to identify monomers, polymers for ring opening polymerization. And you should, by this time in the class, polypropylene should be one of those things in your memory bank. I know polystyrene's in there. Lots of people have gotten that because we talk about polystyrene a lot, but make sure some of these easy polymers are right there. You're going to definitely want that on the final exam, so you're able to identify monomer and polymer units. Good. All right. So the only way in this class that we can control the stereochemistry of the polymer is with this type of polymerization called coordination polymerization. Now, we didn't study this in detail. It was tacked on to the stereochemistry unit, but in free radical polymerization and in condensation polymers or step growth polymers, you know, we didn't talk a lot about stereochemistry because in general, those types of polymerizations don't lead to tacticity unless you do something special in step growth polymers and you build the chiral carbon into the one of the monomers. However, in coordination polymerization, which is a different type of polymerization for chain growth, so this is chain growth, which means we use monomers like this, polypropylene, polystyrene, etc. Because of this coordination between the Ziegler-Natta catalyst, shown right here, it's a very funny stereochemical type of arrangement. That's how we get stereochemical control. So we didn't talk about the steps, we didn't talk about anything else, but you should be able to connect the concept of stereochemistry and all its features with this idea of coordination polymerization. And one famous type of coordination polymerization is called Ziegler-Natta polymerization. So it turns out you can have stereochemical control with other types of polymerization, like ring opening metathesis, that also won a Nobel Prize in addition to Ziegler-Natta polymerization. So control of stereochemistry is a really big deal in polymer science. It's gotten 2 Nobel Prizes, different ones so far. And the people who won for ring opening metathesis, Professor Grubbs, Yves Chauvin, and I forgot the third person. I'd have to look. Shirakawa, sorry, Professor Shirakawa. They're still alive. You can go talk to them about stereochemical control of polymers at the ACS meeting that's this week. All right. Any questions on this? Any comments? All right. Last clicker. And I will give you back 2 minutes in the sun. All right. Don't forget about dienes. So how do we know that this monomer is a diene, other than I'm asking about cis-1,4 addition? How do we know a diene is a diene? Yes.
2 double bonds.
It has 2 double bonds that are what? What's special about those double bonds? Yes. They're 1 bond away from each other. So this, has 2 double bonds, right? But this doesn't do diene polymerization like we've talked about in this case. And so make sure you know the difference between the two, because what's the DF of this top structure in chain growth polymerization? 4. What's the DF of a diene? 2. That's why it's different. So these are conjugated. Sometimes these are called conjugated dienes. So the question is, which is the correct structure of cis-1,4 for this monomer? So we need to put down the carbon numbers. 1, 2, 3, 4. I numbered it that way to get the substituent on the lowest number. You all remember that from organic chemistry. That's all great. And the question is, where is this substituent and what does it look like? So 1,4 addition, there's going to be 4 carbons in the backbone. So it's not that. It's not that. This is looking tempting. Could it be that one? Or could it be that one? Which repeat unit is it? Everyone has their guesses in? So cis-1,4 addition is this. This one is not correct because remember, this substituent is on the wrong carbon. So if we look very carefully, 1, 2, 3, 4, 1, whoops, sorry. 1, 2, 3, 4. Now we have the substituents in the right carbon. All right, I'll see you on Monday for the review. Please get your homework in. Enjoy the weekend.